Now, of course, if I want to compute the area trapped between two curves, r equals f of theta and r equals g of theta, and the lines theta equals a and theta equals b, then it's the area bounded by the curve r equals f of theta and the lines theta equals a and theta equals b, in this case minus the area trapped between the curve r equals g of theta and the lines theta equals a and theta equals b. So applying the formula, I get a simple formula for this area. It's 1/2 the integral from a to b of f of theta squared minus g of theta squared, where f of theta is larger than g of theta here. Let's apply it. If I want to find the area of the region that lies inside the circle r equals 3 times sine theta, and outside this cardioid in red r equals 1 plus sine theta, I can apply this formula. So it's 1/2 the integral from a to b of f of theta squared minus g of theta squared, where a and b are the angles where these two curves meet. The two curves intersect when the values of r are equal, so when 3 sine of theta equals 1 plus sine theta. And this gives us 2 sine theta equals 1, or sine theta equals 1/2. So we see that there are exactly two angles between 0 and 2 pi, with sine of theta equals 1/2. There are theta equals pi over 6 and theta equals 5 pi over 6. So our formula becomes 1/2 the integral from pi over 6 to 5 pi over 6 of 9 sine squared theta minus 1 plus sine theta squared. And when I expand that 1 plus sine theta squared and cancel, I get 1/2 the integral from pi over 6 to 5 pi over 6 of 8 sine squared theta minus 1 minus 2 times sine theta. I'm breaking up this integral and using the half angle formula for sine squared, and then evaluating at the endpoints, I find that the area between these two curves, between the angles pi over 6 and 5 pi over 6, is equal to pi.